Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So in this module, we're trying to understand how the operating system manages the CPU by providing this abstraction of a process over the CPU. And within this second module, we are currently on the second topic, that is process address space. So within this topic, through a series of videos, we are trying to understand what is the address space, how it is organized, right? What are the different sections in the address space, right? So in the previous video, I introduced the stack section. That is, we understood why do we need the stack section in the process address space. So now in this video, I'm going to continue the discussion over the stack section and talk about how the stack section is actually implemented, how it is actually used to like during the execution of your program, how the functions are represented in the stack section. So it is done by something known as stack frames. So let us understand what are stack frames and how they are used during the execution of the functions. And without further ado, let's get started. So in the previous video, we understood why do we need the stack section. We understood that we need the stack section for the execution of the functions. Now in this video, we want to understand how exactly those functions will be executed and how will the stack section be used. What is the mechanism behind that, right? So as we can see, the stack section is implemented using something known as stack frames. So now let us understand what are these stack frames and how they are used to execute the functions. So basically this is the process address space and this is the stack section. And now the thing is that every function call in the program is represented by a stack frame, right? So we have talked about this in the previous video also, right? So basically the code that you write or the program that you have, it is a collection of functions, and whenever the execution is happening, it is happening inside some function body, right? So during the execution of the program, there are a series of function calls, there is a chain of function calls, and every function call in the program during the execution is represented by a stack frame. So there is a very important point to note here is that I'm not talking about the function code, I'm talking about the function call, right? The same function can have multiple instances, it can be called multiple times, and the stack frame is used to represent the function call, not the function, right? So every function call in the program, when it is executing, it is represented by a stack frame. So as you can see in this example, let us say there is a program where we have three function calls. Okay. So the function one, let's say it calls function two calls function three. And as you can see, for every function call, we have a stack frame. So what is a stack frame? Basically, you can think of the stack frame as a data structure which contains all of the relevant pieces of information that is necessary to describe a function call, right? This concept is very similar to the process control block. So in one of the earlier videos, when we were talking about how can we represent a process, right? There we said that in order to represent a process, we collect all of the relevant pieces of information and put that into a data structure, which is called the process control block. In a similar way, here what we are doing, we want to represent a function call. So we will collect all of the relevant pieces of information, all of the associated data, and put it into a data structure, which we call the stack frame, right? And for every function call, you will have a stack frame in the stack section. So now let us look at what are the different pieces of information that can be part of the stack frame. Understanding that will give us a better idea of how the stack frame looks like. So now we will look at the different pieces of information that can be part of the stack frame, right? So here, let's say we have a stack frame, and if we have a closer look, then these are the different pieces of information that constitute the stack frame. So let's go over them one by one. The first important piece of information are the function arguments. So whenever we make a function call, we supply some arguments to that function, right? And these arguments are like the input data for that function, and the function uses the arguments to perform the computation. So basically, the arguments of a function define its behavior, and they are very important to when we talk about a function call. So for every function call, the arguments are definitely stored in the stack frame. Then there are local variables. So we have talked about the local variables in the previous video also, right? What are these local variables? Basically, if you look at the function body, then there are certain data variables that are defined within that function body, and the scope of these variables are that function body. So basically, the function uses these variables to perform the computations, to store intermediate results or the final results, and these variables are part of the function and they are local to the function. So these variables are the local variables, and all of them are stored on the stack frame, right? Next comes the return address. So the return address is basically the address of the instruction from where the instruction execution will resume after the current function returns, right? So let me explain this. Let's say we have this program, function 1 calls function 2, and when function 2 returns, so from where will it resume the execution? Basically, let's say at instruction n in function 1, there is a function called to function 2, then the instruction execution will resume from instruction n plus 1. Okay, when the function call 2 returns. So the address of the instruction from where the execution has to be resumed after this current function returns is the return address, and we store that in the stack frame also, because when the current function for which basically when the current function returns, then this stack frame can be used to find out the return address from where the execution can be next resumed. Then the final piece of information that is stored in the stack frame is the previous stack frame pointer. So as you can see, for every function we have a stack frame, okay, and there can be a chain of function calls. So in the stack section there can be several stack frames at any given point in time, right? And when the current function returns, the let's say the function 3 is going to return, then this stack frame will be removed, right? And then the stack frame 2 will be on the top of the stack. So when the current function returns, we want to go back to the previous stack frame because it stores the context of the execution. So when function 3 is finished, we want to execute in function 2, right? So this stack frame 3 actually stores the previous stack frame pointer so that it can go to this previous stack frame. So frame 3 will store a pointer to stack frame 2. Stack frame 2 will store a pointer to stack frame 1, and so on. So whenever the current function returns, it can resume execution in the previous function call. And so we need the data, we need the context, that is the stack frame for the calling function. So this pointer is basically to the previous stack frame. So now a very important note is that these are just a indication of what are the different kinds of fields that can be part of the stack frame. This is definitely not exhaustive in nature. I have just included some of the important fields that are part of the stack frame. There can be many more fields, right? It depends on the runtime or the operating system, right? So this is basically just to give you a basic idea of what are the important pieces of information that can be part of the stack frame. So now we have a good idea of what is a stack frame. It is a collection of all the relevant pieces of information that is associated with a function call. Now, another important point is that, which you might have guessed, is that for every function call, we push a stack frame on the stack, and for every function return, we pop the stack frame from the stack, right? So in this example only, when function 1 is called, when we push stack frame 1 with all of these relevant variables or data that is associated with function call 1. So that is stack frame 1. Then function 1 calls function 2. So we push another stack frame for function call 2, which is the stack frame 2. So for every function, we are pushing a stack frame object onto this stack section. And finally, when function call 2 calls function call 3, right? So basically, I want to say when function 2 calls function 3, then we push another object for that particular function call. So that is stack frame 3. And when these functions return, the reverse will happen. These stack frame objects will be popped out one by one, right? So this is how the stack frame behaves. And as you can see, in the previous video, we talked about how the function call executes, how there is a chain of function calls, and how they follow stack behavior, that is last in first out. Whenever there is a sequence of function calls, then the function which was called the last in the sequence, that is the first one to return. And in the same way, you can see the stack frames are basically being used to model the functions, and they replicate the same behavior. The stack frame object that is pushed last, or which is on the top of the stack, will be the first one to be popped out, right? So this is how the stack frames work. Now we have a good understanding. So now let us take some examples. Basically what we will do, we'll take the same examples that we talked about in the previous video and see how the stack frames are used to execute those functions. So let us see some examples. So now let us start with the first example. So what we are going to do, we are going to take the same examples that we took in the previous video, right? So in the previous video, we took two examples. One was the product of two numbers, and the second example was the factorial. So we are going to take the same examples. There we were trying to understand how the execution of functions displays the property of a stack. Here, what we are going to do, we are going to follow through the execution once again, but here we want to understand how the stack frames are used to represent a function call, and how does the function execution take place over the stack section. So here we have the same example from the previous video, that is the code that is used to multiply two numbers. Let me quickly recall the this piece of code. There is a main function in which we are trying to compute the product of two numbers, that is 2 and 3. For this, we call the multiply function. So multiply function takes two arguments, x and y, And instead of directly returning x into y, it is performing the product by repeated addition method. It is accumulating the number in a variable, that is result. So in result, what we are doing, we are trying to add x to result y times. We are in order to compute x into y, we are adding x to the result y times. And for computing the sum, we are using another function. It's a very simple function which directly returns the sum, that is, it takes a and b as input and returns a plus b as the output. So this is a brief description of this piece of code. Now let us see how, when we execute this piece of code, how the different function calls are represented using the stack frames. So now let us start the execution of this piece of code. Here we have the process address space. Initially, when no function call has been made, you can see the stack section is empty. Okay, so let's start with the main function. Let's make the first function call. Okay, so as you can see, when the main function is called, we have pushed a stack frame corresponding to the main function, right? For every function call that we make, we will push a stack frame, and when we return from that function, we will pop the stack frame. And as you can see, I have only shown the arguments and the local variables. Basically, main function does not have any arguments, and it only has one local variable, that is the prod variable. It is an integer which will finally store the product of the two numbers. I am skipping the return addresses and previous stack frame pointer for the sake of simplicity of this diagram, right? But nonetheless, we can still understand this example with this limited piece of information, right? And what we will do in the next video, we will take a full-fledged example where we'll show all the different fields that are part of the stack frame with a complete example, right? That we will do in this next video, but for this video, we'll keep it simple. We are only showing what is necessary to show. Okay, so this is how the stack frame looks like for the main function. We don't have any arguments and we have one local variable. Now let's call the multiply function. So when we call the multiply function, as you can see, another stack frame has been pushed on top of main. So this is how the stack frame looks like for the multiply function. It has two arguments, that is x is equals to 2 and y is equals to 3, and it has one local variable, that is result. And this is an integer variable that will again store the product of x and y. So it is initialized to 0, as you can see. Now after the multiply function has been called, it calls sum function 3 times. So every time it will add 2 to the current value of result. So let's add 2 to 0. Let's call the function sum. So when the sum function is called, we push another stack frame. Sum has two arguments, that is a is equals to 0, the current value of result, and b is equals to 2, that is the value of x that we want to add to result. And now what we will do, we will add these two numbers, 0 plus 2. So sum has only one local variable. It is not named. Basically, we do not have a name for this location, that is, we're just computing a plus b. The value of a plus b will store here, but we do not have a named variable. Okay, so a plus b will compute the result and return 2. So when 2 is returned, you can see the stack frame for this sum function has been popped off. Okay, it has been removed from the top of the stack. And as you can see, the same property that we noticed in the previous video is being followed here. The function which was called last in the sequence is the first one to return, right? So the stack frame which was pushed just recently, that is the sum function, has been popped first. So this is the stack behavior. Now the result of the value of result is 2. We will add the value of x, that is 2 again. So sum is called again with different arguments this time. So a is equals to 2 and b is equals to 2. Previously, it was called with a is equals to 0 and b is equals to 2. So here we have a very important point to make, is that every stack frame is unique. It is for a function call, even for the same function, when we are calling it with calling it different times, right? Previously we called sum with different arguments. This time we are calling it with some different arguments. So the basically the stack frame is a representation of the function call, not the function. Every time the function is called, we will have a unique stack frame, right? So this time the value of a is 2, b is 2, so we'll return 4. So again, when the sum returns, the stack frame is popped off from the stack. Now we'll make one final call to the sum function with the value with the arguments, that is a is equals to 4 and b is equals to 2, and the computed sum will be 6, which will be result to the multiply function. So now the sum function has been done. It was called 3 times. Every time it was called, we pushed a unique stack frame, and when it returned, we popped off the stack frame from the top. Finally, it's time to return from the multiply function. So multiply will return the value 6 to the main function. The stack frame for multiply has been removed or popped. And finally, when main returns, its stack frame is cleared, right? So you see how this piece of code was executed on the stack section. So now you have a clear idea of how this portion of the address space, that is the stack section, is utilized for the execution of the functions. So now we'll take one more example, the example of the factorial function, right? This is somewhat different because it is a recursive function. So let me quickly recall the factorial program. So here we have a main function, and here the result is used to store the factorial of a number. We call the factorial function with the number 3. We want to basically compute 3 factorial, and the way we can compute the factorial for any number n is that if the number is 0 or 1, then it is a base case. We just return 1. This is the base case of the recursive function. And otherwise, we can compute n factorial as n into n minus 1 factorial. I've already described this program in detail in the previous video also. So this was how this piece of code works. Now, the unique thing about this code is that it is a recursive function, right? What is a recursive function? Basically, any function that calls itself is a recursive function. So here you can see factorial, this fact function is calling itself, right? So now let us see how this function will be executed using the stack frames. So now let us start the execution of this function. Again, like the previous time, we have an empty stack section in the beginning. So this is the part of the address space, right? So the first function to be called is the main function. So let us call the main function. And again, just like previous time, just like the previous example, we are only showing the arguments and the local variables. So for the main function, there are no arguments in this case, and the only local variable is the result, right? So we have a local variable. So this is how when the main function is called, we have pushed the stack frame corresponding to the main function. Now the main function will call the factorial function with the argument n is equals to 3. So again, we'll push the stack frame for this factorial with n is equals to 3. So the arguments are n is equals to 3, and there is only one local variable which will be used to store the value of fact n minus 1. It is not a named variable, but this will be a temporary result, fact of n minus 1. So this is the local variable, okay, which will store the result of n minus 1 factorial. So when we call the factorial function with n is equals to 3, we can go through the logic. And so 3 is not equals to 0, 3 is not equals to 1. So in order to compute 3 factorial, we have to do 3 into 2 factorial, right? So we'll have another function call. So this time factorial function will be called using the value, using the argument n is equals to 2, right? So now you can see the interesting thing here is that since this is a recursive function, we are calling factorial from itself, right? And every function call is uniquely represented by a different stack frame. So both of these stack frames are for the same function, but they are different function calls. This is for argument n is equals to 3. This is for argument n is equals to 2. Even if the arguments are the same, even then different function calls will be represented using different stack frames, right? So now let's continue with the execution. So in order to compute 2 factorial, we again do not hit the base condition. We go again 2 into 1 factorial. We will call factorial function one more time with the value n is equals to 1. And this time we will hit the base condition. You can see when the value of n is 1, we can trivially return 1, right? This is the stopping condition for this recursive function, okay? So when we hit this base condition, now we'll start returning. So factorial that is called with the value of n is equals to 1 will now return. This function call will return, and it will return the value 1. And when that return happens, the stack frame which is on the top of the stack, that will be popped off, right? So when the value of 1 is returned, we can compute 2 factorial. So the result will be 2, and 2 will be returned. So this factorial which was called with the argument n is equals to 2 is now returning. And again, we remove the stack frame. So the value that was returned is 2. And now we can compute 3 factorial similarly. So the value of 3 factorial is 6, which will be returned to the main function. We remove the stack frame, and now finally it's time to return from the main function. Main function returns all of the stack frames are popped off from the stack. So you can see how the stack frames work. We took a different example this time. We took a recursive example. We saw that we understood that the stack frame corresponds to a function call, not the function. Even if there are multiple function calls with the same arguments to the same function, for every time there will be a different stack frame. So we'll take one final example, the same example, but in a different way. So for example 3, we have the same piece of code, but what I have done is that I have removed this base condition. Basically, I have commented out this base condition to show you an interesting thing. So what happens if there is no base condition in a recursive function, right? You might know that there is a stack overflow, right? You might have encountered this error when you do not put a base condition. There is infinite recursive. The recursive function calls itself without stopping. It calls itself infinitely, and there is a stack overflow. So you might have seen this error, but let's see this error working through an example through this figure, okay? So now we don't have any stopping condition. So let's start the execution of the program again. We are computing the same thing. We are computing 3 factorial, but without any condition. So main will call factorial of 3. just like the previous time. Factorial of 3 calls factorial of 2, factorial of 2 calls factorial of 1. As you can see, there is no stopping. We'll keep on calling factorial, but we cannot call it indefinitely. So what happens next? What happens next is that when you call factorial of n is equals to 0, what the stack has done, it has crossed its limits. So basically there is a fixed limit, a fixed amount of memory that is allocated for the stack section. Although you see that the stack section is growing and shrinking, but it still has a limit, right? It has a limit in the sense that beyond that point, if it crosses, then it is an illegal operation. So that is a stack overflow. So the stack, the data that is pushed, that has been pushed onto the stack section, is now beyond what was allowed. So this is a stack overflow. Generally, as you can see, the stack section size is fixed, that is roughly 8 megabytes. After that, we have stack overflow. So within the 8 megabytes number, if if the stack section remains within that number, then it is fine. But if we push more objects on the stack, which basically pushes the limits, which basically goes beyond the defined limits of the stack section, then we have a stack overflow, and this is an illegal operation. And when this happens, this is basically an illegal event. When this happens, the program is killed, the process crashes, right? So guys, this was it for this video. In this video, we understood how the stack section is actually used, how it is actually implemented using the concept of stack frames. So now we have a clear idea of why we need the stack section, how it is used, right? So this was it about the stack sections. From the next video onwards, we will look at the other two remaining sections, that is the heap section and the data section, right? So this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.